So the goal here is to show that continuous functions are Riemann integrable. Continuous function. I just say integrable. And here we will learn many things about continuous functions themselves, which we had missed, which we did not do last when we were doing continuity, because it may not have seen, it may have seen out of context. Right? So that's one. So let's see. So do you guys know how you prove such things? Have you done this? So let's set it up. Let's see. So f is, so we'll begin by taking it on a closed interval, but obviously for integration, it doesn't matter whether it's a closed or open interval. But we'll begin by taking a closed interval. So R is continuous. Right. So we want to say, basically what we want to say is that the epigraph has a well-defined area. The epigraph has a well-defined area. 0 to 1. So any ideas how we can show that it is integrable? Just tell me something that I can get started with. See, till now we don't have any theorems. Okay, we do not have any theorems. So we have to start with the definition. Right? Find a bound in that area. Okay, what I don't understand the last thing clearly, but let me take a partition and write the maximum and minimum and so on. So let's take a partition Pn. Now you guys know what I mean by Pn. Okay, I mean a partition in which every part has length 1 by n. Okay, and it is okay to consider these partitions. It's we have shown that and it's formed. Okay, so Pn means regular partition. I mean, certainly, with a subset of partitions, we can show that the difference is going to go to 0 of the upper and lower sums, and that's obviously good enough, right? So they don't even need what we did last time. Regular partition, but I'm just writing this clearly of length 1 by. Okay. Then I will just write this upper sum and lower sum. Okay. So you let me say f. Usually I will not say because f is the only function here in consideration, but upper sum. I'll immediately write upper sum minus lower sum. Okay. Because that's what we want to show, right? We want to show that the difference goes to 0. I mean, that is the only way to say that the limit exists, kind of. Okay, rigorously speaking. Well, that's not the only way, but this is. So we take the upper sum and we take the lower sum. But let me expand. So, I mean, obviously, you guys know what upper sum means. I have to take part. Let's say, for example, this part. And we have to take a supremum and infimum. But in this case, since it's continuous, there will be a minimum and maximum that all of us know. On a closed interval, it will have a minimum and maximum. So maybe this will be the minimum, this will be the maximum. You can take the boundary point. So let's write it as a summation. Let's see. So this bad notation. 1 to let's say yeah, it will go till n. So this will go to n. So upper sum. So maximum I will denote by this. Okay. Okay. I will have to multiply this with the length of the interval, right? I mean, I should do k plus 1 by n minus k by n, but the difference is just 1 by n, right? The length of the interval, that rectangle. So, okay. Sorry, Chandan, are you trying to join again from a different, because it just disappeared. Yeah. Okay. Okay. Fine. All right. So let's see. So let's continue. This. Is it clear till here, everyone? Just think I'll just summarize the whole thing again and just I'll finish this. I don't want to do this in the class. Okay. Yes. So today's goal is to start, getting classes of integrable functions. Okay. So continuous functions are integrable is what we want to show. That is the first class of functions which we know should be integrable and we want to show they're integrable. So we start with the definitions and we take the upper sum and lower sum and we basically want to show that the difference uh, goes to zero, right? That will tell us that both of them tend to have a limit and they have the same limit, which is so it will do two things at the same time, right? That's the key thing. Uh, okay, and so for that we're taking these regular partitions. Okay, and yeah, yes. So we want to show integrability, right? So that is basically saying that we want to show that this upper sum minus lower sum. We want to show that this thing goes to zero, right? By taking large enough n or by taking finer and finer partitions, same thing. You want to show that it goes to zero. So you agree that's the meaning of integrability, right? That upper sum and lower sum should go to the same place. And there are, as I said, there are important things to learn here about continuous functions themselves. In fact, one of you sent me a question this week, which was exactly that thing about continuous functions. We'll see. It's needed. Yeah. So you mean this summation? Yes. So that is the upper sum, right? This is the upper sum. So okay. So this yeah, capital MK I need to say. So basically, I take the kth interval, right? That will end at k by n and begin at k minus 1 by n. And in this, I need to pick the maximum and the minimum. So the maximum is capital MK, and I need to put that in the upper sum, right? So yeah, so I pick that interval, I pick the maximum f of mk, let's say it's here in this case, f of capital MK, and then I multiply it with the length of the interval, but in this case it's just 1 by n. The ultimate goal is to show that you can make this difference smaller than that. That's the way to show that, because there's no formula of limit that you can use here. I mean, this is an arbitrary function to that extent. Yes, that's what we have to use. So we have to show that given any epsilon, you can find the n such that this difference becomes less than that. Right. Let me just, since I think let me just write this in a more brief way. I'm writing the same thing. This is so remember this is a finite summation. At every point, it's a finite summation. Although if you allow for infinite summations, then you can do anything. At every point, it's a finite summation. Given any epsilon greater than 0, show that x is n such that u, I just say Pn minus n is less than epsilon. You see, this is really what it means to show it's less than 0. Sorry, that it goes to 0. The difference goes to 0. Because this is not a known quantity like sin x or some limit. You have to do it by the definition. This thing. So, what is the obstruction? Yeah, I'm saying, what is the obstruction? What is stopping you from showing that this can be made less than? I mean, why don't we just say that take n big enough? Yes, why not? I'll just write the n outside. Okay. If you want to make this less than epsilon, then well, one thought will just be to take n big enough. Why does that not work? That will obviously not work. Otherwise, every function is integral. But I don't need to, right? Because it's already positive. And each term is positive. So what we just need to show is writing the same thing. Is that this difference can be made less than n times epsilon. That's all you need to show. So there is fm1 from the first part in the partition. We have this plus the second part contributes. That is a natural way to show, right? So I mean, it doesn't imply that, but that's how we will show it, right? Otherwise, it's very strange. Yeah, not just difficult, also very strange if it happens. Well, difficult maybe. Yes. So as Raghav has said, so he has gone for the, what's the natural thing, right? The natural thing to get from here. So I've not done anything till now, just writing the same thing again and again, right? The natural thing to do, I mean, that should hold, right? It's a good theory, decent, not strange theory, classical theory also. It should happen that each term is less than epsilon. I mean, it would be enough to do that, right? I mean, that should happen. So we will try to go for that. We'll try to show that. Yeah. So essentially, given any epsilon, you want to figure out a partition so that the difference between the maximum and the minimum in each part is less than epsilon. Why? Is that the definition of that? At different points you may need different deltas. Yes, least delta, existence of least delta. Do you think it's, yeah, it may not exist, right? If so, let me just all of us see this, but let me just say what is the question from here. And what Rasul has said is correct, but the reasoning I feel is incomplete. But what we will just need to show is this fact. Okay, I'm not writing it, I'll write it again. Given any epsilon, given any distance, epsilon, given any error, you want to basically figure out a small enough delta, or small enough 1 by n, a large enough n, right? You want to figure out a small enough delta, small enough, make the partition small enough so the difference between any 2 points in that small enough neighborhood is less than epsilon. Okay, because maximum minus minimum is less than epsilon means that difference between any 2 points in that small enough neighborhood is less than epsilon. We want that kind of size. It should work for the entire interval, make sure. Okay, then we'll be done, right? And that is what we have to show. So let's write that, because that's kind of a separate theorem. But now we kind of see the need for it, and we will see how that is not just continuity. It turns out to be the same, but not same also. Let's see. This is what we want to show. So right. Let me write it in full. Okay. Given, because this is a new kind of thing about continuity. Maybe. So, given f, we write that also. Continuous. And again, given epsilon, and try to see how this is not just continuity and how smallest delta is not so obvious that it exists. Given epsilon greater than 0, find, or not find, but just we can't find it, but show there exists a delta greater than 0 such that whenever you take 2 points small, distance is small than delta, means if the partition size is in delta, it will work. So such that x minus y, any x minus y, it's not like around the given point, less than delta. Just keeping it straightforward, and this is what we have to show. So you see how this is not just continuity. In continuity, given a point, given a point, we do it. Given a point x naught, and then you have a value. Around that value, we choose an error, and then we find a delta which works for this point. Right? We take a delta and something like this. You see, then it works, right? Then you take this delta around this x naught, then it works. But we want to find one delta that works for everyone. For every point, there are infinitely many points. Yes. Only continuous. No. Yes, but the maximum slope, yeah, need not exist. So those are stronger types of continuity. What you're referring to, maximum slope, is called Lipschitz continuity. So there, yeah. And this is a regular exercise also. This thing less than 10 times. D epsilon by a minus b, b minus a. So what is that? Yeah, but that's the same thing we are trying to show. We are trying to show what they have said, just claimed, or I don't know, declared. So maybe in that book they have already proved this fact earlier in the continuity chapter. If it's a, so what we are trying to show is called uniform continuity. That is much weaker than this Lipschitz continuity. But let me not discuss those nuances now. Those are a different topic. But the point is that finding a smallest delta is not such obvious thing. So you may take every point. Well, again, I'm saying the wrong thing. Okay, finding the smallest delta is the wrong concept. Showing that the smallest delta exists. Even if for every point you try to take the biggest possible delta, which you can take and still remain. Epsilon is fixed throughout. Epsilon is fixed throughout. Epsilon is not changing. There has to be one delta that works. Epsilon is fixed throughout. Yeah, but that minimum may be 0. That is the problem. A priori, right? We don't know. because it may not be a minimum. Uh, infinite slope is because the word slope is not so well defined unless it may have a infinitely increasing. It may the slope may be finite at every point, but it may be increasing and increasing. Yeah, so it doesn't happen in a closed interval. But for example, if you take the function, if you take the function, let's say like this on open 0, closed 1, x going to 1 by. Now this is a continuous function, and the slope is finite at every point in the interval in the domain. But you see that you won't get a smallest delta because as you go close to 0, I mean, so if you even just put epsilon equal to 1, now find the smallest delta. It does not exist. You will need to take, so does everybody see that? If you take epsilon to be just for this function, so that's why basically the closed interval is has a very rich properties, basically, which are not well understood. So when this is a situation, the slope at every point in the domain I have given is existing, is finite. Okay, but you cannot find the smallest delta, right? Because I mean, if you are at a point which is, let's say, 1 by 10 to the power 10, then around this point, right? Around this point, the delta has to be less than 1 by 10 to the power 10, right? Yeah, for the difference to not change. I mean, so if you want, you can just write that. If you want 1 by x minus 1 by 10 to the power 10 to be less than 1, then you can check. I mean, you cannot really, have that change in x has to be really small. Okay. Oh, sorry. So this is 1 by 1 by 10 to the power 10. Right? So you can understand. Okay. So, that's, the point is that you have to change very, very small, and that change has to be smaller and smaller. Okay, as you go close to 0 because the velocity is. So yeah, there are problems. So, but you cannot find a counter example in a closed interval because it does not exist. So there is a smallest delta in a closed interval. For a given epsilon fixed value, there is a smallest delta. There is a delta that will work for every point. So yes, it's called uniform. Yes, on a closed interval. So yeah, so this is called. So why is this called why? So if so, this property, if you assume this property for a second, why is this called uniform continuity? Because there is one delta which works uniformly for all the points. Okay, this property when we prove this, okay, after we have proved this, this is given a name. It's called uniform continuity. Uniform meaning same delta. So yes, that's what we are going to prove. So we're going to prove this, and this is called uniform continuity. So continuity implies uniform continuity. Okay, but on a closed interval. Okay, but those are just words. How will we prove this? No, no, it is not right because we could not find the smallest. But it was not on a closed interval. That is so that's the whole point. Existence of limits will be used in the proof. Yeah, let's see. Let's try to prove this. There are many ways to prove this. Many ways. We'll try to do. Let's see what way we end up doing. But how do you start such a proof? That's the question. How do you start such a proof? So closed interval 0, 1 is kind of like a finite in a lot of ways, it's like a finite thing, in a lot of sense. It's like a finite set. Set theoretically, it's obviously infinite, it's uncountable, but analytically speaking, it's like finite in a lot of ways. Mhm. Oh, sorry, whole thing has the epsilon. Uh, mhm. No, no, no. So that is okay, okay, okay. Okay, okay. We make only one interval. Yeah, then the difference will be just the maximum minus minimum of the whole function. So that could be anything. Mm, mm, mm. Yeah. Yes, it's continuous, so it has to be bounded, right? Yeah, because on a closed interval, so it has to be bounded. Right. Bounded. That also, yes, that also. Mm. Mhm. Yeah, yeah, that seems like a, yeah. So let's divide it at half. Yes, okay. Uh-huh. Yeah, but I don't know how that will help you to find a delta that will work for all points. That will kind of help you to show existence of some special point like Riemann one, right? Because it will like converge to a point. But what we are trying to show is a global property, but that also, but I don't know. I think what you're saying can work. Yes, f of 1 minus f of 0, or maximum minus minimum. Um, oh, um, how do you write it? So, so I mean, maybe, so are you trying, so it can be like something like this, like, so the whole interval does not work because the maximum, like, so let's assume that this is more than epsilon. Otherwise, we are done. Then you divide the interval by half, and then we assume that half also does not work. Okay, so half also does not work means that at least one of the subintervals may, the difference between the maximum and minimum is more than epsilon. Yeah, whenever the difference is less than delta. No, that can never happen. I mean, all epsilons mean that for any epsilon, no. So I mean to say that for any epsilon, there will exist a delta depending on that epsilon. For all epsilon, but it will depend on the epsilon. Then obviously, you can't change the epsilon. Delta will not change. Yeah, then delta will also change. But, so that's what I'm saying. So we throw the discussion, the epsilon is fixed. We are not changing. Okay. No. But epsilon is fixed means epsilon is arbitrary. It is arbitrary and fixed, right? We cannot assume anything about it, but also we are not changing it. So when we prove it, something about that epsilon, we have proved for all epsilon because we didn't make any assumption. Uh-huh. You get epsilon meaning? Okay. No, we cannot. Okay, if we say epsilon was half. Mhm. Yeah, but how will that help? Right? Because you need to. How will that? I was thinking of bisection argument, but I think that also does not work. So what I was thinking is, so this is an idea that is used in many proofs, but that's what you can see. So assume that this on the whole interval, the maximum minus minimum is more than epsilon. So the whole delta equal to 1 doesn't work. Now you divide it into two parts, and for each, now if uh, so I mean, if in one of the parts the difference is more than epsilon, then again we can zoom in on that part and go further, right? Because then we are saying that the half does not work. Delta equal to half does not work. But what might happen is that in this portion, for any two values the difference is less than epsilon, and in this portion also the other from half to 1 also, given any 2 points the difference is less than epsilon, but that doesn't imply that the difference between any 2 points is less than epsilon, does it? No. I mean, it doesn't have any relation. It could be very far, right? As you can see. I mean, this half point may not be good because this two could be very sorry. You can understand. So yeah, so I'm saying that the this thing holds. So this thing holds uh, for all x comma for all x and y in 0 to half, and also holds for all x comma y in half to 1. If this happens, then that does not imply that it holds throughout. Yes. Okay. I mean, still, one can say something that then there are 2 points. I mean, so, but first let me clarify this. Everybody understand this. Yeah, this is the problem. If this was not the case, then we could kind of do another bisection, and get some kind of contradiction. Does everybody see this? So this method works when for a lot of proofs it works. Here it is sort of not works. But it does imply something. It does imply that maybe given any x comma y, it does imply that f of x minus f of y is less than 2 epsilon. But it's not useful, it's useless, but it's just an observation. It's less than 2 epsilon for all x comma y in 0. I hope you guys can see this. This is like this comment, this matching. Is that uh-huh. Is this let's see, let's think. Yeah, it's true. So if you have this to this thing, then it does imply that the global difference cannot be more than 2 epsilon. It's not useful for the proof, I think, because 2 is a big problem. But does it, can anybody explain why this is true? And on the right side also. But then I'm claiming that it implies it just means that the difference between any two functional values is less than epsilon. In 0 comma 1, in 0 comma half, and also in half comma 1. Epsilon is fixed throughout. So just yeah, that is that we can just yeah. So can anybody explain why this is true? This is a good, I mean, this is just follows from an intermediate value theorem. It's 2 epsilon thing. Mm-hmm. And y is in the other. They have to be in different parts. It cannot be in this. Mm-hmm. Yeah, this part. Mm-hmm. Half. Yes, yes. It's just a simple addition, right? Yeah. And all yes. And this, so I think I was wrong. It does not even need intermediate values. No, it doesn't even need that, right? That is just it's just a theoretic thing. This is as an epsilon, and similarly others we add. So that is not useful in this case, but it is just a, you know. I'm just removing this. It is useless. So this bisection, I'm not saying it doesn't work, but I cannot make it work. So now, so let's give this some direction, because this is a very this is a question which can be done by many ways, and it is done by many ways in the literature. If you see, there are many proofs of this. Yeah, but then it's 2 epsilon, right? That is not good. I mean, the 2 is a big problem, you see. Then the 2 will become 4, and then that's not good. Yeah, that's yes, right. I don't feel that it's good. Yeah, I mean, again, it might work, but I doesn't feel good. Hmm? So no, but for what partition is it true? That is the problem. If it is true for some partition, like the difference is less than epsilon, then obviously it's true for bigger, for increase n, it will remain true, right? Because the upper sum will go down and the lower sum will go up. That, but you have to show that this happens for that, and that's the major. Okay, so I've been stressing on. Hmm? Yeah, so you're saying for some delta or some partition. Uh, hmm. Yes, that's right. So you have to say for any delta or for some epsilon u. Yes. So we have to say that for f. So let's assume that no delta works, right? That's what we have to do, right? So let's assume that for any delta, no matter how small you take, there will always be a pair of defaulters for that delta. And take a smaller delta, there'll still be a problem. Problem means that you understand, right? There will be some 2 points which are close enough by delta, but their values are more than epsilon. Okay. Now, what I'm trying to say that what Vasuga has said, that is essentially the only way. Well, logically also that's the only way to do it, because see, in the end, you given epsilon, you cannot find the delta, right? Given epsilon, you cannot find that delta in terms of the epsilon. It doesn't follow like that. So to understand the nature of this thing, then you would also know how to approach the proof. So it's not because in analysis, in the end, the epsilon delta arguments are not difficult once you are comfortable, but you should know what to prove. And that's what we're trying to understand. What we are trying to prove here is something non-constructive. Simply put, it means that in the end, you're not going to arrive at something. In the end, you're not going to give a delta, that the delta has to be epsilon square or has to be epsilon cube or has to be some. There is no such thing. It is not connected to epsilon in that way. There is no connection in that sense. So you're not going to make anything in the end of the proof. So it means that the proof cannot be a direct proof. Okay? What you will show that it is that you're not going to show that this is true. You're going to show this is not false. Okay, so you will say that by contradiction, that if no such delta exists, then there is a problem. You cannot directly find that delta, so you cannot do it. So then at least we can get started. And once you get started, then a lot of things get done automatically by the language. So assume that no such delta works. So contradiction is what we are going to do. But obviously the proof is not done by anyone. Let's see. Uh, contradiction. So assume for so again epsilon is through. Assume that for any delta greater than 0, for any delta greater than 0, there exists x minus y whose distance is less than delta, but the distance between the function values is more than this. That's simple. Now where do we go from here? So it's like I'm taking smaller and smaller delta, but I'm ending up with some point where the gap is more than epsilon functional values. Divide that meaning. But that may be even bigger, right? That can tend to infinity. Yes. Yeah, that can. No, no, no. It can tend to infinity. So you guys can think of. So can you guys think of function? Yeah. So that's it's a little. We think that it cannot. So we think that on a closed interval, the slope cannot tend to infinity. Right. This is a very interesting thing actually. So because the example I showed was not on a closed interval, right? So you will think, but so we think that this is a very interesting point actually. On a closed interval, continuous and so on, we think that slope cannot tend to infinity. Can anybody give a counter example? It's not difficult. Think in terms of derivatives. Or another, this slope cannot be infinite. Even that is not true. The slope can actually be. So what do I mean? I mean that you have a closed interval, you have a continuous function on the closed interval, but the derivative is infinity at some point. Come on, someone give me an example. Yes, which one? What is that? Uh, from uh, uh, okay, okay, like this, like this. Okay, okay, okay. Uh-huh. Since the convexity. Okay. Yes, yeah. Basically, it can happen. Yeah. So you see that it can, even if it's continuous, it can happen. Okay. I'll go down that part I don't understand. Uh, mhm. Oh, okay. Yes. So that's certainly an example. You can even give a differentiable example, as I said. Right? But this certainly works, right? What's wrong with this? It's correct. It's continuous, and this slope is correct. That's certainly, you can just take the quarter circle. So this is it's going to get vertical, but you can just take so it's being slope in the sense that you yeah, this one. It's not differentiable, but the slope is infinite. The left derivative, if you want to say. So this one. If you take a quarter circle, then it gets vertical, right? That place. If you take the, I'm not sure. I mean, the left derivative one has to check, but is it infinite? I think it is infinite, right? We just take the equation of the quarter circle and check it. Yes, I think it should work. But you can just simply take square root of x also. You see, right? If the derivative is 1 by some at 0, doesn't exist. It's infinite. Right? It's even differentiable. Yeah. Yes. Correct. Yes. That's what I'm saying. Yeah. Root x. But yeah, it's not differentiable in that sense. But anyways, so that can happen. It becomes infinite for a very small time, but so yeah, so this basically what we have proved is that the uniform continuity does not imply Lipschitz continuity. The slope is not bounded. Area basically that's a good question. I'm not going to use the words, but okay. So what do we do from here? We cannot use the slope in that way. So see, for any delta, so what does it mean? It means that if I take delta equal to 1, it does not move. If delta equal to 1, there is some point x1, and I'm just calling it x1 and y1, right? So you see, I don't even need a mind. No, I have to write this thing. This thing is more than epsilon. Then I say I'll take delta equal to half. Okay, but still it is not what. That's right. So you don't have to take all deltas. That's what he's saying. Is a sequence of deltas will exist going to zero, for which it will fail. And I mean, for that failing, it will implies that it does not work for any delta because we are taking a delta going, we are taking all possible delta in some sense, right? You agree? Because for any delta you take, you have a delta smaller than that in the sequence. So, anyways, this you get the sequence is important. So you see, in this way, you get these things where this difference I'm making less than n. This so forget about the partition integration thing. This time is this n, but still we are getting. You see, we have brought things down to sequences. And intentionally, we are doing it like this, but class would have spotted this. But this was my plan also. Because there are other proofs which don't use sequences. And those proofs have a lot of advantage. They can be generalized to places where sequences don't work. But in reals, sequences work because you have a dense subset, a countable subset of rationals. Or simply put, you have sequences towards any point. You have this. So zero, you have sequence going to zero. So the sequences and limits are everything can be said in terms of sequences. But where is the contradiction? For every n, xn minus yn is getting smaller and smaller. But xn yn is changing, right? They're also changing. That's the whole point. It's the same thing, right? So far, we have just rewritten the thing in that sense. That it's basically what is happening is for you're taking this delta, but then you're finding a place where the gap is more than delta. And you're taking another smaller delta, you're finding some other place where the gap is more than epsilon. So that's not a contradiction directly by its own. You have to use the fact that you're in a closed interval, 0 to 9. Closed interval is important. We have a sequence of xi's and sequence, but one thing is true, yeah, a sequence of xi's and sequence of yi's, they smaller, their gap is becoming smaller and smaller. And so you have two sequences which are going towards the same place. We want to show that the functional values will also go towards the same place. Well, are they going to a place? That is the question. The gap is becoming smaller. So you have two sequences, but whose difference is becoming smaller and smaller. But are they going to some place? If they were going to some place, then you are done, right? So if if we had that, but we don't have control over this. But if we had this, if this goes to some L, right? Well, obviously that implies that the y's also goes to some L. So from here, can anybody complete? If we assume this, if we assume that the xi's go to L, then obviously because of the limit, the y's have to also go to L, right? You can use this. You can let n tend to infinity. Okay, has to exactly has to become less than epsilon at some point, right? So that implies by continuity. So that is the thing, that this goes to FL and this is by continuity. This also goes to FL. But then what does it mean? That the gap has to become less than epsilon, right? So the x size goes to FL means that, let's say, some x thousand minus L is less than epsilon. So epsilon by 2 doesn't matter. That you will realize when you do it. And some y, let's say 10,000 or something largest of those. That epsilon by 2 trick you don't have to do. You get 2 epsilon, then you will realize. Okay, because you're not going to get 4 from there. Right? So, but yeah, then this difference is less than epsilon. So we are done, right? Because then you have found the end at 1000 for which the gap is less than epsilon, which is a contradiction. So the whole thing rests upon limits. We want to show that the sequence of xi's maybe have a limit. Maybe. Hmm? Hmm? Just one x1 one by one is enough for us. Yeah, so there may be several. Uh, okay. Mm, yeah, okay. Okay. Yeah, but that's what we're trying to do. Yeah, that is the same question actually. Right. That's a similar question. And that is a kind of, again, a property of, same property of closed intervals called compactness. Or, but yeah, that if some intersection of some things is empty, then some finite intersection is. But that is a little, then they have to go to a different approach than sequences. Not trying to go there because they not rethink something. But yeah. No, not to same place, but that is true, right? If the exercise, as I've written, if the exercise converges to some place, then everything follows, right? Maybe, yeah. I mean, that would be good to show, right? That the exercise are convergent. Is that right? Does everybody see that? That if the exercise are convergent, that implies itself that yi's are also convergent. Yes, that's the problem. But this was just a wishful thing. That if they are convergent, then that's right. Yeah, so the extent may not be convergent. That is a problem. Yeah, but that doesn't mean it becomes empty uncountably many steps. It could be an uncountable set. Right. That is a but yeah, that's right. Everything follows from closed interval, but that is what has to be said clearly. But yeah, there are so many things about the closed interval which we don't know, which I don't know, which you guys don't know. There are many things. That's the beauty of the closed interval. Many strange things happen from the fact that it's a closed interval. Obviously, we have underlying similarities. Closed interval is a very good place. So you have to show that the xi's are convergent to limit. That will not have to show, but that would be good. But the xi's need not be convergent. But so all of you know some theorems. I mean, so now we are trying to reason in a, I mean, just get to it in a, somehow. Like, theorems where we have convergence of sequences is guaranteed, or monotonic subsequences is guaranteed. Come on. Yes. So how do you use it? Tell me. That's right. Exactly. And that's all you need. You need a convergent subsequence. And more easily, to say it more easily, is that this xi's have a monotonic subsequence. I mean, that is just a discrete question. It can be proved by just original principle type arguments. We have done that earlier. I'm not going to do that, but I'm just saying the xi's need not be convergent, but there will be a monotonic subsequence in that, increasing or decreasing. One of them you will get. But that monotonic subsequence on a closed interval has to be convergent. You just take the supreme. Okay. And that's basically the Bolzano-Beer stress, that it has a convergent subsequence. That's all. And then you work with that subsequence. No, that's it. Is that right? Do the whole thing for that subsequence. Okay. So there will be this xi1, xi2, and so on that converges to some L. And from here, so you can take a common subsequence if you want, but it will be the same because of the gaps. The difference between them is going to 0, right? But that is not important. You can take a common subsequence. Okay. But it is fine, right? You see that if this is converging to L, I think now you already see it. I'm just going to say it. This thing is less than 1 by k, 1 by I k. You see that this will also converge, right? Take limit k to infinity. So the same subsequence y will also work. Otherwise, you can take an intersection and then you have to do that. As long as you have finitely many sequences, you have a there will be one subsequent, like kind of one index which will make all of them converge. So maybe different places, but here they'll converge to the same place because of this theory. And then just, I mean, basically now that is the problem is reduced to that subsequence. That sequence is the subsequence. That subsequence, I mean, the sequence is now that subsequence. Okay, so everything will just repeat in the same. So it's not a difficult question. Okay, it is not a, but there are elements in this which you have to understand. What can be done, what cannot be done. Like realizing that this, in some sense, has to be done by contradiction. Like obviously, you may read some proofs where it will seem like it's not done by contradiction, but you will see that they will use some result, but to prove that result, they would have used but proof by contradiction. That. Which converges. Okay. So I mean, then just repeat the whole thing again. So basically, my point is that you can assume that now this is your sequence. Is that right? And you can just say that this is your sequence: Z1, Z2, Z3. Right. I mean, so it's almost like the same question again, but assuming that the xi's are convergent. We can forget them. It's not a problem, right? Yeah, it doesn't hold. Yeah, it doesn't hold, but that's not the problem, right? I mean, once you find out, so yeah, so you, so see, it doesn't matter because you have this thing going to L, right? But this implies that the yi1, yi2, this also goes to L. right? Because the xi minus yi, the gap is less than 1. So this will also go to L. But that you can take F now. You see, everything just works as it, because in the end, you just want to get a pair of points for which you get a contradiction, for which the difference is less than epsilon. That's all, right? You get this F's. Yeah, right. You'll get a pair of points for which the gap will become less than epsilon because you have convergence. Yes, yes, yes. No, so it is just that, see, so you take any sequence, it has a convergent subsequence, right? So, okay, so before that, it has a monotonic, it has a monotonic subsequence. Yes, yeah. I mean, even CS version of that is true. Like if you take a sequence of length, let's say 100 square plus 1, then there will be a monotonic subsequence of length 100. So there's a finite n square plus 1 sequence has a subsequence of length n plus 1, which is monotonic. Ah, any sequence. In any partial order, those kind of things are also true. But anyways, okay. So you have a monotonic subsequence, but a monotonic subsequence on a closed interval will have a limit, right? Because you can take the supremum of that. Is that so? Does everybody? Yeah, because the closed interval is important here. Otherwise, the limit may be the end point. But then there'll be a problem. We want the limit to be in the set. Otherwise, okay. So I just think about that point, but at least it's okay if it's in the set. So you get this subsequence I1, I2, right? And you can take the supremum of that, and that is the limit. But that supremum will be in the closed interval because it's like the maximum of the set. The maximum has to be in the closed interval itself. And that is good. That is good. That's what. So does anybody see in what cases this will hold if this was not a closed interval? In what cases will this theorem hold if it was not a closed interval? So you're saying it's not a closed interval, and is that so? Can you say? So I was just thinking that we use the in the proof we use the fact that the limits are existing, but we didn't use the fact that the limits have to be in the closed interval itself. Oh no, we used it, right, because this sorry, yeah, we used it because otherwise this FL, otherwise these may not tend to FL. Uh, uh-huh. Yes, yeah, and that was important. Yes. So that's what I realized later, just now. So assume that, I mean, let's say you were in an open interval and the limit was at the end point, right? That's, we have to assume it's an open interval, otherwise it will be inside. So if you take an open interval and let's say the limit L was here. But the point is that if the limit is here, then this sequence doesn't tend to any point in the domain. So the range values of this sequence are not obligated to converge to a point. They can shoot off to infinity. Ah, yes. Yes, the limit doesn't exist inside the open interval. No, it exists. It always exists in R, but it doesn't exist in the open interval. The limit exists. Because it's a bounded interval. So when you're taking a monotonic subsequence, its limit will exist. But it can be the endpoints in the worst case. But the problem with being, that is fine. Yeah, that can happen, but that's an ad hoc thing. The point is that that's ad hoc, right? That's not under your control. Uh, mhm. Yes, yes, that's right. Then this argument will work. That's correct. Yeah. So that's with the limit being inside. Yes, but you see that can happen. So that can happen for some functions. That can happen for a lot of functions. For every epsilon also it can happen. Yeah, that's right. But it doesn't have a good description because for an open interval there will always be a sequence whose limit is not in the open interval. That's right. Yeah. For any open interval, there will always be a sequence inside the open interval whose limit will not be inside the open interval. Might not feature in this. Yes, that's right. That's right. Yeah, that's correct. So I'm not saying that functions on open intervals cannot be uniformly continuous. That can certainly happen, right? A function which is on an open interval can be uniformly continuous. Why not? That can happen. But yeah, functions on a closed interval have to be. It will still be uniformly. Yeah. So, okay. Um, yes. So that's what we kind of done today. So maybe we can. So let's stop here today, certainly. And but I just give a few things which you guys can think about. Uh, you can just think about this. So, so if so f on this open interval, I think this is correct. So a comma b to r is uniformly continuous if and only if f can be extended to this continuous. So there is a continuous function on closed a comma b which agrees with this f on the open a comma b. So you can assign two values at the end point so that the resulting function is continuous. So you can think about this. That's, yeah, so that it becomes continuous. It's kind of one direction is okay. This thing, both directions are the same. And here is another thing. Okay, maybe in this one. So it should be true. If it is not true, then it will be true for closed intervals. Let's see. happen, then f of, yeah, maybe, yeah, this is the right thing. Okay, f of a Cauchy sequence. So f of xi is Cauchy. It is defined Cauchy if xi is Cauchy. And Cauchy means that basically the difference between the terms of the sequence can be made arbitrarily small if you make the terms arbitrarily big. What does it mean is that given given epsilon greater than 0, there exists n naught depending on epsilon, such that for all points bigger than n naught, for all points n minus, so the difference, I'm not saying the sequence is convergent. I'm just saying that the difference between the terms becomes less than for all n and m bigger than 1. So given any degree of smallness, you can go far down in the sequence so that beyond that point, the terms are in epsilon band. That is what the sequence I say, it's a Cauchy sequence. Okay? So I'm saying that, so continuous functions take convergent sequence to convergent sequence, very good. But uniformly continuous functions do more. They take Cauchy sequence to Cauchy sequence. Okay? And convergent sequence is surely Cauchy, but Cauchy is not necessarily correct. And also, I think the converse might be true. I think so. That's it. I'll stop here today. Try them. Yeah, because yeah, I couldn't take classes this week. Try to be more regular. Yeah. Just a few things. I had some things this week.